Today's topic will be hydrogen technology in thermal analysis. And before we start with the topic, I want to introduce myself. For those who have not met me in any past webinar session, my name is Sebastian Seibt. I'm the head of laboratory for the application laboratory here at Linzais in Germany. I'm chemist and I'm working for Linzais since 2013. And you can contact me by my mail address if you have questions directly. You can contact me here at s.seibt@linzais.de. For those who do not know the company yet, the Linzais Thermal Analysis was founded in 1956 by Dr. Maximilian Linzais, the guy on the top left picture here, in the middle of Germany, in the right northeast of Bavaria, in the city of Selb. This is also the place where we are located nowadays and where our main manufacturing takes place. Besides that, we have subsidiaries and facilities in the US, India, and China, where we do maintenance and service, where we do a little bit of training, and of course, sales. In all other countries of the world, we have representatives and distributors who are distributing our instruments more or less, and you can get in touch with your local dealer if you need some equipment, if you need a quotation, or if you have any service request all over the world in those countries where we are not represented directly. In the meantime, our company is owned by the son of our owner, Mr. Klaus Linzais. You can see him in the middle picture over here, and his two sons in third generation, Dr. Vincent Linzais and Mr. Florian Linzais, who are building the management of our company nowadays. Our main business area is, of course, the manufacturing of measurement instruments for thermal analysis, also thermal conductivity and thermoelectrics, and of course, service testing in our own labs. On the picture on the right side here, you can see one of our labs where the dilatometers are placed, for instance. A short overview of our product range. As said, we cover the complete range of thermal analysis, beginning with calorimeters, or in thermal analysis, we speak about differential scanning calorimeters, which is shortly named DSC. We have thermal balances, thermogravimetric analyzers. We have the simultaneous thermal analysis, which consists of a combination of a balance and a DSC unit. We have various dilatometers for measurement of coefficient of linear expansion, for measurement of length change at all. We have thermomechanical analysis, a broad range of thermal conductivity measurement instruments. We have thin film analyzers. We have devices for thermoelectrics, Hall effects, thermal conductivity of thin films, of coatings, which is a field where we focus a little bit on. And of course, we have a lot of customization. So all these instruments can be customized. They can be equipped with water vapor generators, with special environments, so adjusted for special environments. They can be coupled to mass spectrometers, infrared spectrometers, and many more. So this is also a little bit where Linzais focuses on. So the customization plays a big role in our company. Today's topic, the hydrogen use in thermal analysis and hydrogen applications in thermal analysis, is also what we would consider as customization. So many of our instruments can be used and operated in hydrogen atmosphere and used for hydrogen applications. The hydrogen roadmap you see on the slide, and what I want to explain as a introduction to today's topic, is what I took from Fraunhofer research group, who created this so-called roadmap for thermal analysis, but for hydrogen technology in general. So the renewable energy and green energy is a big topic nowadays, and the hydrogen circle you see here is more or less showing what applications and what use hydrogen can be used for and can be useful. And as you see, the goal, or the circle, consists of the renewable energy that creates somehow hydrogen. So you create electrical energy and transfer it into chemical energy, or you transfer it into hydrogen. So you have a hydrogen production as a first step. Then the hydrogen, once it is produced, needs to be stored, needs to be transported, needs to be exported, or wherever you want to use it. So the storage and transport are the other issues. And then, of course, the last big field is the use of the hydrogen, which can be as a fuel cell, can be as an engine, can be also technical. And in every one of these sections, thermal analysis can be used for research tasks, for quality control, or for even experiments that simulate the processes that you are looking or this circle is aiming at. In words, or as a better overview, this so-called roadmap, as I said, taken from the Fraunhofer research group, shows a little bit where hydrogen research is done or is performed and what goals are tried to achieve by hydrogen research nowadays. First of all, there's a lot of research in the electrolysis. So the electrolysis is where the hydrogen generation or from renewable energy into hydrogen is where the electrolysis takes place. So hydrogen can be generated out of water by electrolysis, and the research field here is taking care of storage, pipelines, platform technologies for hydrogen generation. It affects the increase of power density and lifetime optimization of electrolysis units, the material optimization of these units, and the optimization of catalysts that are used in electrolysis. Then there's the industry. The industry, of course, has research tasks where the hydrogen use in production is useful or can be used, for instance, for sinter metals, for sintering in hydrogen atmospheres, of course, for chemical reactions and so on. There's research in the development of methane pyrolysis, so another source for hydrogen, for logistics, and also there are some other fuels that affect hydrogen, like ammonia as a fuel that's easier to transport and store and easier to handle. There's development of high volume storage capacities and so on. And then, of course, there are the other fields like power generation and traffic. Traffic, of course, there's the fuel cell. Hydrogen storage for mobility is different than the hydrogen storage for industry. There's the question of on-site hydrogen generation, cooling techniques, fuel cell production itself. And on the field of power generation, there's, as I said, the complete range of renewable energies, on-site concepts, integration of hydrogen storage and networks, or power storage in form of hydrogen in general. And this is where the research nowadays takes place. And everywhere where there's research, of course, there's also thermal analysis. So just as an introduction and overview, what hydrogen research means and where it is used. I want to show you now step by step these 4 big fields and what kind of thermal analysis equipment could be useful in the given field. At the very beginning, as I said, there are the renewable energy sources. Here in Germany, we abandoned the nuclear power and we are trying to switch and transfer to solar power and windmills and geothermal, so green energy sources at all. However, these green energy sources are mainly dependent on sun, and as sun is shining only at day or wind is not always blowing, the availability of power and the availability of electricity can be crucial. So therefore, a transformation of power to hydrogen or to any other fuel may be useful. So the transformation from electrical power to chemical power may be useful. These green energies, as I just mentioned, are mainly consisting of, as said, windmills, solar panels, geothermal plants, biomass, water, and so on. And the general goal is the reduction of carbon dioxide emission. As said, thermal analysis can play a role in material science, and of course, all these types of energy source, like a windmill, have somehow to be optimized, have somehow to be built. And the first example I want to show you is, in this case, the thermal expansion measurement by dilatometer of, in that case, composite materials. So this is a little application where the linear expansion or the expansion of composite materials is shown. It's a quality control, and 2 different composites of similar similar content or similar behavior are investigated. And as you can see, the expansion is quite similar, but with a little difference. When they get soft, when the glass transition is reached here at around 200 centigrades, they differ a little bit, which can be crucial if you want to use that kind of composite, for instance, as a windmill blade. That can be effects that could affect the stability, that could affect the behavior when they are under stress, when the wind is blowing and when they are moving. So optimization of stuff like windmill blades, of course, can affect thermal analysis. So it begins really at the, as I said, at the power generation, at the green energy source. The same for solar panels. So expansion and electrical conductivity of solar panels could be a goal for thermal analysis. where we could do some measurements. Another quite interesting thing I want to show you is the electrical analyzers also affecting polymers. If we stay at the example of the windmill blades, if you have a composite consisting of maybe carbon, maybe polymers, you could investigate the curing of the polymer. For instance, as you can see here, this is the curing of an epoxy resin. And as you see, the dielectrical analyzers is kind of consisting of an instrument with a sensor, with this black sensor cable. The sensor is applied directly to the liquid resin. And once it hardens, you can see the dielectrical constant. It goes to a maximum here at the so-called CP3, the maximum reaction rate, that shows you the more or less curing reaction. And when the curve goes down, the curing ends. And at the end of the cure, you can define the end of curing when this reaction rate comes to a lower level. And using this can be showing you or shows you the optimization or the optimum curing time and when your polymer is finally cured. So this is just another example where the thermal analysis could be used in the hydrogen circle. The next step beside the generation of energy itself would be the transformation from electrical to chemical energy, like I mentioned before. As I said, storage of electrical energy is quite difficult because you need a big battery and the power density within the battery is rather low. So storing electricity is not that easy. Storing a chemical, however, or energy in form of a chemical is easier to achieve. Therefore, electrical energy can be transferred into a chemical energy by transferring it via electrolysis in that case. Maybe if you do electrolysis of water, you see on the scheme on the left, in general, how electrolysis works. You have a DC source, you have an anode and a cathode, and then you have the electrolyte. In that case, it may be water. And the electrolyte, once the power is applied, the electrolyte is dissolving into cations and anions, creating oxygen and hydrogen. In case of water, you would collect the hydrogen and waste the oxygen, and then you could use the hydrogen and store it somewhere. Electrolysis is always a direct conversion of electrical energy into chemical energy, and it's quite useful and quite a useful technique. The only thing that makes it difficult and a little bit complex is that you need a lot of power, and the figure of merit and transformation rate is rather low, so you lose a lot of power due to heat, which should not be is not the ideal case here. Therefore, the electrolysis can be or has to be optimized. Where a lot of research is taking place, and again, this is a field where thermal analysis can be useful. For instance, for optimization of all the compartments of an electrolysis cell. Like in that case, this is an example of, again, dilatometry, where platinum wires or the expansion of platinum wires are investigated. It can be also used for investigation of cathodes and anodes to monitor the aging, or more or less the shrinkage of the cathodes and anodes during electrolysis. Once they are used, they lose a little bit of surface material. So if you use them for a long time or quite often, they get thinner and thinner, and once they are at a critical range or critical mass, you have to exchange them. And this could also be monitored, for instance, by dilatometry. An alternative method to transfer electrical energy into chemical energy, besides things like electrolysis, would be also coal gasification or biomass and charcoal as a hydrogen source. You could generate hydrogen out of biomass and charcoal if you use water vapor in combination with biomass. So there will be a reaction with the available carbon with the water steam, forming hydrogen, forming carbon monoxide, carbon dioxide, or even methane gas. Of course, this has to be done at very elevated temperatures, very high temperatures, at a certain pressure. And doing so, you need to fire a furnace. Usually you do that electrical. So bigger furnaces can be also, of course, used or fired with fossil fuels. However, if you want to transfer electrical energy and chemical energy, just imagine you have an electrical process giving you access to the bound carbon and biomass or charcoal, transferring it directly into hydrogen. The experiment can also be done in a thermal analyzer. In that case, for instance, in a high pressure thermobalance, or in that case, a STA that also monitors the DSC signal. So if you use biomass, in that case, charcoal, instead of biomass, but any carbon containing material, and then you add water vapor at elevated temperatures, you see that there's a loss of volatiles at the very beginning. Then you add the water vapor at around 80 minutes here, and then there's a huge mass loss taking place. So the red curve is showing you the mass loss. Once the water vapor here is applied, the sample loses a lot of mass, which is the mass of carbon that is gasified. The carbon reacts with the water steam and forms hydrogen and carbon monoxide. So the equation is shown here at the right side. So carbon and water forms carbon monoxide and hydrogen. So this is also a method to transfer electrical energy into chemical energy, a set that can be monitored or can be optimized using, in that case, a thermobalance, or like in that experiment here, Lindsay's STA PT1600 high pressure. You need a little bit elevated pressure for that kind of experiments, and you need elevated temperatures. As said, these processes are very often optimized using thermal analyzers and then performed in a big scale or scale up to a big reactor. The next step in the hydrogen circle is the storage and the transport possibilities. Once you have your hydrogen created, you want to use it, you want to transport it, you want to store it somehow. And there are different methods to do that. As said, hydrogen storage is a little bit easier to achieve than the long-term storage of electrical energy. So electrical energy requires a pretty big, pretty heavy battery, and hydrogen or any chemical can be transported as a liquid, maybe as a solid, as a gas, depends. For hydrogen itself, the storage options are usually once you have it, you can do it, put it into a bottle, in a pressure bottle. You can do chemical storage like a sorption experiment, or store it by chemical reaction with any other material. Maybe you have a metal powder that takes up the hydrogen that can be pressed, or as I said, you can directly fill it into a bottle. Each kind of storage method has advantages and disadvantages. So I will begin with the gas bottles. So just pumping the hydrogen and pressing it into bottles is pretty easy to achieve. These bottles can be used and transported quite easily. However, they are only for short-time storage, as the disadvantage of hydrogen is the high diffusion rate, and these bottles will lose a certain amount of hydrogen by diffusion. So if you store them, you have to store them at a very safe place. There should not be fire or light sources or open fire sources close to them, because the environmental air and the hydrogen that diffuses out of the bottles could cause an inflammation or even explosion. So it's a little bit risky. That's by the way, the reason why hydrogen bottles are not so frequently used in mobility. Besides that, there are other ways like sorption on maybe metalloorganic frameworks or porous materials like zeolites or something like that, where you can sorb hydrogen within the pores that such a material offers. So if you look at the metalloorganic framework, like in the picture up here, there are very frequently pores or gaps within the material where a gas could be adsorbed. There is interaction between the gas molecules and the carrier here, and the gas will be kind of trapped within these pores. And therefore, a metalloorganic framework or a zeolite or certain ceramics can be used for storage of hydrogen. Then you have a solid that contains a certain amount of hydrogen, and you could release it by temperature, you could release it by chemical reactions, by pressure, or by evacuation. However, the release is sometimes very tricky and difficult to handle, and this is where the research takes place, and where also thermal analyzers, for instance, thermal balancers, can play a role. Besides that, there's of course also surface sorption, like on various metals. In that case, I have an example for titanium. Titanium hydride can form by just reacting titanium at elevated temperatures with hydrogen. Therefore, you have chemi-sorption at the surface of titanium, and titanium hydride will form. This is easier to handle. However, it's a little bit more dangerous, like with the bottles. These hydrates are flammable. They can cause explosions and fires, and the controlled release of the hydrogen is also rather difficult. So this is where the problems are in the storage, and this is where the research also takes place. As promised, there are some examples for thermal analyzers again. What we did and what we do is sorption experiments with high pressure thermal balances. In that case, this is the STA high pressure 1 and 2. This is the floor mounted system that can handle up to 300 bars with a rather big sample volume. And in that application example here, you can see the sorption of hydrogen on a platinum aluminum catalyst. And in that case, the heat flow was monitored. So this is not the gravimetric signal. This is just the calorimetric signal showing you the heat of sorption of hydrogen on a platinum surface. So this is at an elevated temperature, at a constant pressure, constant temperature. You put the hydrogen onto the sample and you see the heat flow over time gives you an indication about the heat of sorption of your surface. By the way, at the same time, you could, of course, also monitor the weight change. Then you would also see the amount of hydrogen that is sorbed at the surface. And therefore, you can get an idea how hot the sample becomes and how much hydrogen per mass or per mass unit can be stored. Once you have stored that, and once you have your hydrogen more or less flexible and you have it mobile, you can use it as a fuel. You can use it in the industries. Depends a little bit what you want to do. So the key issue here is the controlled hydrogen release. If you want to use hydrogen as a fuel, the easiest way or the common way is a fuel cell. As you see on the video image over here and the fuel cell scheme over there, a fuel cell is more or less a reactor that allows a controlled reaction between hydrogen and oxygen. If you just would burn the hydrogen, of course, it will also react, but then you create a lot of heat, and you want to have not that much heat. You more or less want to have electrical energy again, because you want to retransfer the chemical energy into electricity. Therefore, the fuel cell is used, and as you see here, it consists of two chambers and a membrane in between. This membrane is where the reaction takes place. So on the one side, the hydrogen is transferred to the membrane. On the other side, the oxygen is transferred to the membrane. Hydrogen and oxygen react at the membrane surface because the hydrogen can pass it. The oxygen molecules cannot pass it. So the hydrogen passes this membrane, reacts at the inner surface and with the oxygen. During the reaction, an electron is released. The electron is by a wire or by this electrical bridge here is transferred into the car or wherever you need it. The electricity of this reaction can be used, and water is formed out of the elements hydrogen and oxygen. So the water that you used for electrolysis at the very beginning is now produced again, and the electricity, the energy that you used to dissolve the water is now can now be used in this process for your engine of your car, the electrical engine of a car, or wherever you need it. And this is a very nice to handle, nice to control process, and is more or less what a lot of researchers are aiming at for using this in a car, for using this in mobility. As said, the critical thing is how to store and controlled release the hydrogen in a mobile storage or in a mobile vehicle or something. But the energy creation by the fuel cell is what's already state of the art at the moment. There are also different fuel cells, not only the ones that operate with hydrogen and oxygen. There are different, you can see the names there, and there are different types of fuel cells. They all have different operating temperatures and different fuel materials. They are not all for hydrogen. They can also operate with methanol, with carbon dioxide, with carbon monoxide. And the electrolyte is not always a membrane out of a polymer. They can also be, like here, a base or phosphoric acid, like acid, or you can have carbonates or also solid oxide. So it depends a little bit on the type of your fuel cell and the fuel you want to use, depending on the application. In a classical electrical car that's driven by hydrogen, usually you use the classical fuel cell with hydrogen as a more or less fuel and as a polymer membrane. So as said, this is the state of the art. I also have an application example for this. As you can see here, this is the controlled hydrogen release out from a titanium hydrate matrix. So this was titanium hydrate that was created before, and this was used in an STA, so in a thermal balance. This one was not using pressure. This was just ambient pressure. And in that case, there was a controlled hydrogen release monitored by temperature. As you see here, during linear heating and linear temperature increase, you can see there is a mass loss taking place, a two-step mass loss between 300 and 500 centigrades. So that kind of catalyst that was used here, that matrix catalyst, released the two-bound molecules of hydrogen around 300 and 400 centigrades. So by temperature, you could control the release of hydrogen. Of course, in a car or in a mobile device, it's not always possible to use temperature for the hydrogen release, but in general, this is how the research may look like and where thermal analysis comes into play and plays a role when hydrogen is used as a fuel. Besides that, hydrogen, of course, can not only be used as a fuel to power electrical cars or stuff like that, it can also be used technical, like in industry, when in that case, sintering or metal sintering was performed in hydrogen atmosphere. In that case, a Linzey's TMA or Linzey's dialectometer was used with absolute hydrogen as an atmosphere, so 100% hydrogen atmosphere. And these samples that were investigated over here were sinter metals, powder metals that were pressed into a little rod. The rod was heated with a certain sinter profile. And as you can see, these metals first expanded, and then at a certain temperature, they started to shrink in a certain way. So the metals reacted with each other, formed a solid body. And for special metals, sometimes hydrogen is required or hydrogen is used because the hydrogen is avoiding oxidation. And these metals do not form the oxides and do not oxidize. They really react with each other. And the hydrogen just covers their surface to form or to guarantee a reducing atmosphere all the time. So this is a typical application of hydrogen thermal analysis when doing sinter studies of sinter metals. So this is where the hydrogen more or less can be used directly also in our instruments. One last word about hydrogen in thermal analysis is regarding the safety. As said, most of our instruments can be operated really in hydrogen atmosphere because the system themselves, they don't care about hydrogen or inert gases or whatever is in there. That's not a problem. The problem is the environment and the operator where you have to take care that nothing can happen and where you have to take care for safety. So if you want to operate our systems in hydrogen atmosphere higher than 4 or 5%, so higher than the flammable concentration would be, you have to use a safety unit. And therefore, we offer a safety package consisting of, as you can see on the scheme below, a burn-off unit, which would be over here. So there is a burner, constant flame. So there's a carrier gas of hydrogen coming out of the system and all the outgassings of the system that are transferred into this flame unit. So they are burned off. So there is no risk that the hydrogen atmosphere could gather around the system or could be created in the room where the instrument is operating. Of course, we have safety interlocks and automatic gas controls for evacuation, for gas control. In that case, there's also a water vapor generator connected to the instrument, as you can see here. So all these valves, all these gas interlocks are working automatically. There's a hydrogen sensor over here. There's another hydrogen sensor directly at the instrument. If there's a leakage or if there would be a leakage, the instrument would automatically flush down and flush itself with inert gas, in that case, nitrogen or argon or helium, whatever is connected, to avoid a critical concentration of hydrogen in the environment. Once these sensors notice that the system shuts down, the furnace shuts down, there's an automatic lockdown, and it's getting flushed with inert gas. So we more or less guarantee that there's no risk of hydrogen release or uncontrolled hydrogen release in the environment or directly to the operator. Besides that, as I said, we can also offer to integrate hydrogen sensors in the inside of the instruments if needed to check the hydrogen concentration within the instrument. And the whole safety package is coming with our systems and can be added to any of our systems, no matter if it's dilatometer, if it's thermobalance, if it's the DEC or any other instrument. So we can operate really almost every kind of instrument series in hydrogen atmosphere if needed. That's just about the safety. And with that, I want to finish this talk. As said, this was just a short introduction where thermal analysis could play a role in hydrogen research, where hydrogen research is focusing on at the moment nowadays, and where there are the, I would say, interactions between thermal analysis and hydrogen technologies. So far about the presentation. I want to thank you for your attention at that point. And if you are interested in a special hydrogen application or need more information about a certain task, about a certain project involving hydrogen, involving one of our instruments, one of our techniques, please get in touch with us. We can discuss that. Let us know. As said, this presentation was just a short overview that we are able to combine any of our instruments with hydrogen technologies, and that we are willing and able to help you with that kind of special applications.